Oh, thanks. Good weekend? Mine was good because I did nothing. I changed the oil in my cars. That was about it. My only excitement was when I put the drain plug back in. After draining the oil in my car, I heard crack! Fortunately, it was just a little nylon gasket ring thing, but you know, I had to get another car to go to the store to get a package of 5 of them. That's great. My car's 1994. The gasket's going to outlast the car, but that's all right. So, I affectionately refer to this demonstration as high road, low road, and we're going to demonstrate it. If you were here Friday, I asked you to think about it. Okay, be honest. Who thought about it? Hey, more than I thought, less than I hoped. Okay. Well, we'll ask you now, just the first half, the first question. I'm going to open polling and let you answer it. Just the first one, first half. Channel 44, polling's open now. If those balls at A and B are let go at the same time, what's going to happen? And the first thing I want to ask you is, both balls reach the end of their tracks at the same what? Do they arrive at the same time? Are they going the same speed? Or do maybe they get there at different times but they're still the same speed, or none of them? Or what do you think? I like this one, as you'll see, because it has to do with forces, motion, acceleration, velocity, change in motion, as well as energy and momentum. So it kind of reviews some of the stuff and momentum and energy that we just finished. I do apologize that this big I-beam's in your way, but I figure you can look around it for... All right, let's see. We got 45 responses. I'm assuming that's most of you. There's a few stragglers that haven't decided yet. So 10 seconds. 10, 9, 8, 7. And I pause for it. You realize I don't count you if you're right or not. I want to know what you honestly think. If some of you are not participating because you're afraid to get it wrong, you shouldn't be worrying about that. I want to probe the class. That's been 10 seconds. One more of you came in. Okay, we're split. 41% and 43%, B and C. So most of you think they'll get at the same speed. And the rest of you think they'll get there at the same speed as well as the same time. Okay. This is good. So if I let go of them, and they roll down, half of you think they'll get here at the same time and the same speed, and the other half of you think, roughly, that they might get at different times, but they're still going to be going the same speed. So now I would like you to discuss with your neighbor, because I want to see if who ends up swaying whom more. And I'll re-ask the question. So it's open. Talk to your neighbor. Explain your reasoning. Who's more logical? All right, get your new votes in. Polling's open, so you can get your new votes in. Only got half of you. I'll speed you up. 10, 9, 8, 7, 6, 5, 4, 3. 16 of you haven't voted. What's up? You don't know now? All right. Okay, we were swaying to the C's there. Some more of you think both now. This is good. So somebody that thinks it's both. Okay, we got to take her here.
Okay, and since the tracks are equal length, if you thought the speed was the same, speed is distance over time. Therefore, if the distance are the same for both tracks, and you think they both have the same speed, the time would have to be equal as well.
Okay, he's going for if the tracks are the same distance, and you think they're the same speed. You remember speed is distance divided by time? So if they're going to be the same speed and it's the same distance, they would have to be the same time. Is that your logic? You want to add to that?
Oh, sorry, I'm jumping again.
Go ahead.
I want to explain
Explain what you want.
they're not the same height, are they?
Technically, they're not the same length. However, I was surprised when I made them. We started out the same length, and then I just bent this one. And interestingly, if I get these right there, the bent one's like a whole inch shorter. I thought it was going to be more. So they're nearly the same length, actually. Well, yeah, it's an inch out of a meter and a half. That's a small effect. Trust me, when you see it, you'll know they're either exactly the same or conspicuously different. If it was an inch difference would make it very close. So it's essentially that one. Okay, well, the answer is, I don't have to tell you, let's do it. Drum roll, please. So the obvious answer is that it's not the same time. They do not get there at the same time. Let's discuss that one first. This one, it gets accelerated down the ramp, then levels off. And how do you think its speed, what do you think happens to its speed from now? Yeah, you can see that it's going at a constant velocity. Minimal friction since it's rolling. This one, and I hope it's clear, they'll be the same. If I can let go at the same time. In this part, but this one drops again and goes faster for a while. But watch this, if I can do it. I'm going to try to match so they match up at the end to make it more conspicuous for you. Let's see. Oh. I go with this one first, okay. They're going the same speed at the end. I'll try it one more time. Right at the end, now, I'm trying my best. I hope you can see it. Ideally, they go the same speed at the end. So the answer was, I can't read it now, was just the speed, B. Now, why is that so? Because this one, the left one, the one closest to me, doesn't change speed. It's going the same speed most of the time. This one closest to you, the low road, as soon as it starts going down here, it accelerates, which changes its motion, change in velocity. So it's going faster than this one most of the time. And if it's going faster, it gets to the end quicker. Some people think, oh, well, it slows back down here. That's true. It decelerates as it comes up this. Do you see that? Which slows the velocity back down. But back down to what? What this one's already going. So even while it's right here, it's going faster than this one. Do you see that? So left hand, faster, 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 stays faster. Slowing back down, but still faster than this one. And so by the time it gets back up here, they're going the same speed again. Now start thinking in terms of energy. If we call this the low road, let's set that at 0 gravitational potential energy, 0 height. How do their potential energies compare here? Right, and that's going to get converted into kinetic. So I'm going to ask you the second question. Answer the second half. When they reach the end of the tracks, do they have the same momentum, kinetic energy, or one or the other, or neither? Polling's open. Your friendly reminder clues if you're getting confused. Let's see. Potential energy has to do with height. The higher something is, the more potential energy it has. The faster something's going, kinetic energy. Energy associated with motion. They transform between one and another. They can.
Do you want us to vote E, F, G, and H, or just E, F, G?
Yeah, it would make more sense if you do E, F, G, H. Yes. If you already hit A, just put in the new one. It just replaces your answer. Most of you have voted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, you had your chance. Most of you think G. A few think B and C, thus really E and F. Okay. So let's see. G was both. So most of you think that both balls will reach the end of the tracks with the same momentum and kinetic energy. You are correct. First clue, way to think of it, if they're, by the time they get to the end, going the same speed, then they have the same kinetic energy. I'm taking the assumption that the balls look the same. They are the same mass. Kinetic energy was 1/2 mv squared, so if they have the same v, they have the same kinetic energy. And momentum is mass times velocity, mv. Same thing, same m, same v. So by the time they each get to the end, they have the same momentum and the same kinetic energy. Look at it in terms of conservation of energy. They both start with the same potential energy and no kinetic. So the total energy's always got to stay the same. So the high road here, it has a little more or less potential. Just it's by itself from starting point. Here to here, more or less potential. Less. Where'd that energy go? Into kinetic. That's why it's moving. It has speed. And it keeps that. This one, same thing at this part, but when it gets down here, it has even less potential, which got converted to kinetic. That's why it's going faster. It raises its potential, slows back down, less kinetic, but it's back to the same point the high road has. Because it's at the same height, it now has the same potential energy, so it should have the same kinetic, because the total has to stay conserved. Does this make sense? Woo, we'll go backwards. There's conservation of energy.
Two objects have the same potential energy, do they always have the same momentum?
If two objects have the same potential energy, do they always have the same momentum? No, because potential energy is just like, right now this ball has potential energy, but it's not moving, so it has no momentum. This ball, if I was dropping right there, right when it falls to the same height, for that split second they have the same potential energy because they have the same height, but this one's moving. So it also has kinetic energy as well as momentum. If something's not moving, no momentum, no kinetic energy. All right, I like that one. Keep it there. Okay. Going to ask you another one. Get you see how you're thinking. Polling's open. 3 baseballs thrown from the top of a cliff along the different paths. If their initial speeds are the same, and you don't have to worry about air resistance, so throw it up, straight out, or down, same speed, the ball that strikes the ground below the greatest speed when it hits the ground will be which one? So throw it at the same speed, different angles. How do the speeds when it hits the ground compare? And you don't have to worry about air drag. Yes? Yeah, A goes up and then falls down. B is throwing out horizontally and then falls down. And C just throws down. Which one's going to hit the ground with the greatest speed? And this is one where you can solve this thinking of motion, our first few chapters, or energy. And my clue is I find energy easier. But either way should get the same answer. This one's a little trickier, I think. There's a few more of you still deciding. That's all right. We'll give you a few more seconds. All right, last people get in. That was as many as last time. Okay, we're split. A and E. More of you with E. So most of you think at the same time, and those that don't think A will. The correct answer is E. Let me start with A. A, you throw it up at a certain speed. When it gets back to the height of your hand, not the ground, you throw it up, comes back to your hand, what speed will it be going? Same speed. Different velocity, because now it's pointing down, but same magnitude. So that's equivalent to throwing it down. So, see, I would have thought most of you would have guessed C, because you're throwing it down. It's going faster. Well, let's just sum it up this way. Energy. They all start with the same potential energy. Do you see that? They start at the same height from his hand. And they all start with the same kinetic energy. He throws them at the same speed. So the total energy is the same for each. You with me thus far at the beginning? So the total energy has to be the same at the end. And what's their potential energy at the bottom? Right before they hit, they have no height. It's right there. The potential goes to 0. So they all must have the same kinetic energy when they hit as well, which means they're going the same speed. They all accelerate down at the same rate. So that acceleration due to gravity changes their vertical velocity the same amount. That's one where when I think of it in terms of motion and velocity, I kind of get confused. But with energy, start at this height, they end at this height. Potential same change, so they got to have the same kinetic. I don't care which way they go, they got to end up the same. Yes? Oh, I just mean falling this way. Yes?
Doesn't gravity pull down at 10 meters per second?
Every second.
Until you hit critical velocity.
Yes, gravity accelerates everything at 10 meters per second every second.
So if you tossed it up and it was coming down, it already gained 10 meters per second.
Yeah, but on the way up, it slows down. So it's like as if, and then it comes to a stop. So it's as if you dropped it from up there. It comes back down, starts gaining up speed, gets back to the same spot you threw it up at, and now it's like you threw it down at that speed. And so it'll keep accelerating at 10 meters per second every second in addition to that initial velocity it has downward at that point.
Okay, I understood your explanation comparing C and A, but B, maybe he's throwing it so much further.
Yes, and that's going to get into what this is for as we move into projectile motion. Almost there. This, the horizontal velocity gets it out this way. I'll be consistent, this way. So he applies an initial force, and that gives it a velocity horizontally. Vertically, it's gravity pulling down, and that starts accelerating it vertically. And so you got two forces going on, right? Once he lets go, there's no more horizontal force, and inertia keeps it moving this way. And it would go straight forever if nothing else acted on it, right? That's inertia. But gravity's acting on it, so it starts pulling it down. And so it starts accelerating at 10 meters per second every second. But since it started at the same height, it's going to hit the ground at the same height as everybody else. It's got to have the same total kinetic energy. And so it'll still be going the same speed just like the others when they get down to that point. Because energy has to stay conserved. It's one of those that, really? But yeah, you got to let that one seep in.
But it seems if it's going further, it would have to be going faster to get there at the same time.
Getting there at the same time.
Oh, they're not getting there.
It just says
That's an...
when they hit the ground, what speed are
Thank you. I should have, yeah, that's a point that hasn't come out yet. He makes a good point. They won't hit the ground at the same time. But when they do hit the ground, they'll have the same speed. A lot like the high road, low road. Thank you for, yes. That probably helps clarify it then. I think there was another one on here I wanted. Was there? Let me no, okay. Let's do this one then. I'm going to explain it. Okay. There's a classic problem in physics, and this is getting into the chapter 2, just projectile motion, where there's a monkey hanging in a tree. I'm going to hang a monkey from over there, and then we're going to try to shoot it. So I got this electromagnet. I might as well do it. How does he do it? Here's my bullet. That's what I'm going to fire. And for this time, I'm going to use a monkey. It's a softball. We don't want it swinging in the trees. We don't want any excuse for missing horizontally. We're worried about vertical motion here. So the idea is the hunter's aimed right at the monkey. As soon as he shoots, the monkey's smart. He lets go of the branch he's hanging from so that the hunter will miss. And so we want to try it and see if that works. Do you see what I'm going to do? I'm going to pressurize this tank full of air, release it. It's going to exert a force for a certain amount of time, an impulse, which will change the bullet's momentum, get it up to a certain speed. Force on a mass accelerates it. When it comes out, it's going to trip this little lever right here, which releases the monkey. So as soon as it comes out, he drops. What will happen? And I'm going to make it a clicker question, because why not? Polling's open. Whoa, I guess, there it is. Will the bullet go above the monkey? Hit the monkey? Below the monkey? Or wouldn't it be fun if it just explodes in midair? This is where I shift the computer lest something goes wrong. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Where'd my cursor go? Great. Okay, gave me my cursor back anyway. Okay. And now. Most of you thought B. You think it'll hit the monkey. Boy, I'm curious to know why you think it'll hit the monkey. Somebody. Yes?
So the same force of gravity acts on both the monkey and the bullet, and if the monkey drops at the same time the bullet leaves the chamber, the bullet will be falling down at the exact same.
Okay, tell me if I'm saying what you're saying. The same force of gravity is acting on each one. So they're going to fall at the same rate?
Yes.
But that one's moving horizontally.
It's still falling down.
But it still falls down at the same time. Anybody want to add or refute that? Wouldn't it depend on muzzle velocity? Do you think it does? The faster it's going, the straighter it goes, the slower it drops? So the faster this goes, the less it accelerates this way? Over a period of time? Okay, that's a thought.
It's going to accelerate downward at the same rate, but if he's moving more quickly out of the muzzle, he's going to pass the point. What he's trying to say is that it'll pass the point at a higher level than the monkey is, depending on the muzzle velocity.
So if he was going fast, relative, you think it'll miss the monkey, go over the top of the monkey? Okay. But they're both falling at the same rate of speed.
Speeding up the muzzle would just make the bullet get to the monkey faster.
So you think speeding up the muzzle, it'd still hit the monkey just sooner?
Yeah.
They wouldn't fall as far, but they'd still hit
Yeah.
by the time they hit? Okay. Let's do it. I'll pick a relatively slower velocity this time. Let's see what happens. You guys ready? 1, 2, 3. Got the monkey. So it does hit it. And the explanations of, yes, gravity's pulling on them, accelerating them vertically at the exact same rate. So vertically, they fall at the same. So it's like this. First second. Chkum, 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 and they hit. Let's try it with a faster velocity. Because if you're going to set this up, you might as well shoot it several times, I say. Now, I don't actually, well, I have a monkey, but he's kind of small. I don't like him. Something a little dumber than a monkey. You know, we're at Utah. We got to do something. Okay. Now, why do I want to get it to not swing? What if it's swinging, exaggerate, like this? When I shot it, and it goes that way, but then it swings this way. You might think it missed, but only because it was swinging. But they still fell at the same rate that first time. So I don't want an excuse of it missing horizontally. Okay, close enough. This time I'm going to pressurize it more, so it's going to come out faster. Okay. Anybody think it will not hit. Because we're going faster now. Okay. 1, 2, 3. Yes, it still hits him, but it does hit a little higher up. The collision happens sooner because it's going faster. They have less time to fall by the time the bullet gets over. All right. You guys are good. This is two-dimensional motion. 2 one-dimensional problems. We got horizontal and we got vertical. Up till now we've done them separately. But when you're projecting things, you get both going on at the same time. However, it should not be any more complicated because the way all physicists solve two-dimensional problems, they break it into 2 one-dimensional problems. I can tell you what's going on horizontally. I can tell you what's going on vertically. Then I can put the 2 together and tell you, some component. If it's going this way and this way, the result's going to be somewhere that way. And you can use math and trigonometry to figure that out. So I got one more for you though. Start thinking of this one. How many hunters are as tall as the tree? Not many. So we're going to put it in. I'm going to hang the monkey up again, but I'm going to lower that end so he's shooting up. Things are changed now. What will happen? Same game, but I'm going to fire it like this. The bullet has to go up first. Okay, who thinks it'll miss? Who thinks it'll hit? We still got more hits. The miss, will it be above it or below it? Above it? There was somebody else I thought that it would miss. What do you think? Above or below? Below. That's good. Split the difference. We're going to be like Galileo and Émilie du Châtelet now. Let's do an experiment and find out. All right, mid pressure. 1, 2, 3. Definitely still smacks Cosmo. And the reasoning, it seems like those half of you didn't vote, but it's like throwing the ball up. As soon as you let go of this, whether I throw it this way, drop it, or throw it that way, what's its acceleration as soon as I let go of it? 10 meters per second every second. And so it starts decelerating, comes to 0, and then starts accelerating down. So it's doing this. But the monkey starts higher in the first place. And so it still hits it because they're accelerating down at the same rate because it was aimed right at it. Good job. Does that make sense? Got questions? Yeah. Good.
Is there some certain formula they use to know where to aim?
You do riflemen's, use a formula. Yes, you can calculate it out using physics. And believe it or not, you guys have enough physics to do so now. I wasn't going to hold you to it. But they don't. They don't sit there and go, hold on. Okay, I'm this far away. This far. My bullet's going this fast. We got this much air drag on it. Okay, I can calculate. Okay, I need to aim 2 feet above. Yeah, that'll work. You can, but there's see, I should have my comic strip of Calvin and Hobbes in a snowball fight. No, it's I forgot the comic strip. Whatever. They're in a snowball fight going whatever, and he's over there sitting there calculating in his bubbles all the formulas that you've seen. while he's getting smacked in the face. Takes too long. So they have an intuitive feel for it. But all riflemen know that if I'm trying to aim at the trash can over there, that I need to shoot a little higher. Because it's going to, gravity, as soon as it comes out of here, gravity starts acting on it. If I aim straight at the trash can, by the time it gets there, it's going to drop some. The faster your rifle, the less it'll drop. The slower the rifle, the more it'll drop. The farther away you are, the more time it has to drop. And so they learn it. It's kind of an intuitive thing, but they don't calculate it, but you can. And in real life, there's air resistance, which means you have to account for that and raise it a little higher still, because it's going to slow down as it gets there. And that is what projectile motion is. Let's shoot something else. Spring-loaded gun here. If I release it, we'll see if I calculated correctly and measured correctly. All right. Almost off horizontally, but we'll just scooch it that way. All right, that was set at 60 degrees. So this is 60 degrees right here. And what that means is this shot out with a certain velocity. What physicists do is break that into components. We give it a horizontal component and a vertical component. And I don't anticipate making you guys do this, but you can understand it. If that's the velocity it's shot out with, the way you do it is horizontal, vertical, and you just drop some perpendicular lines. Guess I can. There you go. So the horizontal part of that is that. You know, you can say V in the x direction. And the vertical part is, these are perpendicular. Vy. And those of you that are familiar with math, oh yes? This is the parallelogram rule that the book explains with vectors. In our case, this was, it's a certain angle, theta. And some of you might be familiar that here's a right triangle. This side's Vy, this side's Vx. You can do the squares. Pythagorean theorem. It's one way to do it. Others know trigonometry, and you can use sines and cosines to figure out. And that's how you would calculate these things, which I don't intend to make you do. But I want you to realize that, at least qualitatively, you can see that the components are less than the main thing that's happening. And let me ask you, when I shoot this, here's the horizontal velocity. As soon as it's released from the gun, what's the horizontal velocity right there, as it's coming along? Do it again. Yeah, we'll be specific. At the top of the arch, what's the horizontal velocity? Right there. Compared to whatever that is initially. More or less? Less. Most of you said less. What's causing it to change its motion horizontally? Horizontally. Air resistance. In real life, air resistance would slow it down a little. Get rid of air resistance. What is it now? It's the same. Inertia keeps it going. Horizontally, it keeps the same velocity. All the way, the whole trip, if you neglect air resistance. Do you see that? Because there's no force acting on it horizontally. Vertically, we'll say the velocity starts out as Vy, that. What is its velocity vertically at the top? Zero. Because it doesn't go up anymore. It stops going up and comes back down. And what's its vertical velocity here compared to there? Neglecting air resistance. It's the same. Remember, that's just throwing the ball up. Throw it up, by the time it gets back down, it's going the same velocity. So when you're doing two-dimensional problems, you do have to keep them separate. Don't get confused between the two, but that's all you do. You just have to do it twice now instead of once. So in this case, this does a parabola. And at this point, well, let's start here. Whoop. There. It's just Vx at the top. And when it gets over here, it's going the opposite direction. And you have Vx, Vy. Here, what's Vx? It's the same, so I can draw it. Vy, it starts as this and it goes to 0, so this is somewhere in between. Let's say there. Those are the components, the horizontal and vertical. You just complete that. There's its velocity. Notice it's a little shorter in the direction it's going. And you can play the same game over here. And you can also look at these as no potential energy, all kinetic. How about here? It has potential. Does it have kinetic? Yes, horizontally it has kinetic. And so you can use the energy game to figure out how fast things are going too, or help you solve some of these. I can do the, let's see, well, I'm at 60 degrees. I have a styrofoam ball. Let's cock it the same force, put it in there. Hopefully you can guess what this will do. Will it make it as far? Air resistance is obvious. It came out with the same initial velocity, but now that air drag gets it. And this one's fun. I'm going to switch it to 30 degrees. Do you think it'll go farther or not make it? Without air resistance. So it was at 60 degrees. Now I have it at 30 degrees. Cock it the same. Who thinks it'll overshoot? Undershoot? A few of you. Same? A couple of you think it'll be the same. Do you see it hit here? Had less time to get off horizontally. Lest you're not convinced. Do it again. So it went the same distance. So if the angle of the pairs add up to 90 degrees, it's going to get the same distance. But which one did it quicker? The lower one. It was in the air for less time. The horizontal component, do you see that because I tipped it? More of that initial velocity it's tipped, so there's a bigger horizontal component. Do you see that? Do I need to draw it on the board? Which means he's going faster horizontally. So he gets over here quicker than the 60-degree one. There's some great pictures in your text in chapter 10 for this, drawing all the vectors out so you can review or go, what are you smoking, Adam? Okay. So the last comment is then, I'm not going to make you do two-dimensional collisions either, but I want to show you. These are two hover pucks. They eliminate friction. Before, we always had collisions that went linearly, straight, back and forth on the air track or whatever. These can do that as well. But most things, like billiards or these, something's already moving, you hit it, and they go off at angles. And my point is, you can solve these exactly the same way as collisions we did on an air track. If you got a ball coming here and another ball comes in, this one's not moving, this one is, and it bounces off and ends up coming this way, but now this one gets moving as well. Well, we'll have it over here. And so how do you solve this one? The way you would do it is just break it into components, the horizontal and vertical. All the horizontal ones, the momentum, total momentum has to be conserved. So does energy. It's an elastic collision, kinetic energy. And then you can do the same thing vertically. I think, does that make sense anyway? I'm not going to make you solve these problems. We always just did it in a straight line, but you can break them into two straight lines and solve all these. You have all the tools under your belt to do so if you need to. You're bored. Questions? A homework question.
Yeah, there was one that said no work is done by gravity on the bowling ball that runs along the bowling alley.
No work is done on the bowling ball rolling along the bowling alley.
By gravity.
No work done by gravity on the ball.
And it said, the selections of the answers said that there's no distance covered by the ball, the force on the ball is at right equal to the ball's motion.
Yeah, I'll jump to it. Gravity is vertical. Does the ball move vertically? Work is force applied on an object to displace it in the direction of that force. If the force is trying to pull it down, but it can't move vertically, up or down, then no work is done on that object by that force. Yeah, so a ball just rolling along, there is a force acting on it, yes. But it's not displacing it in the direction of the force, so no work is done on it by gravity on this ball. Yeah, it has to be displaced. Okay.